Welcome. PSM 201, Study Section 8. Introduction to Correlation and Regression. Introduction. One of the main objectives of conducting analysis is to understand how two variables are related to one another. The most common type of relationship is a linear relationship. For example, you may want to know what happens to one variable when you increase or decrease the other variable. You want to answer questions such as, does one increase as the other increases, or does it decrease? In this study section, you will learn to measure the degree of a relationship between two variables. Both correlation and regression are measures for comparing variables, in that both methods are ways of quantifying the relationship between an exposure variable and an outcome variable. Correlation quantifies the strength of a relationship between two variables and is a measure of existing data. Regression, on the other hand, is the study of the strength of a linear relationship between an independent and dependent variable and can be used to predict the value of the dependent variable when the value of the independent variable is unknown. Learning outcomes of study section 8. At the end of this study section, you should be able to calculate and interpret correlation coefficient, describe the process for and create a simple linear regression model. Correlation analysis. Correlation coefficient is a numerical measure of the degree or extent of linear relationship between two quantitative variables, say x and y. When these variables are normally distributed, the Pearson's correlation coefficient is used, while the Spearman's rank correlation coefficient is appropriate if not normal. Examples of such investigation include relationship between maternal weight and baby's weight, CD4 count and age, blood pressure and body mass index, and so on. Correlation coefficients are useful statistics for several reasons. They do measure the strength of a linear relationship between two variables, which can support a hypothesis about a cause-effect relationship. Additionally, correlation coefficients can be used to determine whether two predictor variables, such as two different exposures, are highly correlated to each other. If they are very similar, then one of them probably does not need to be included. In most cases, plotting of scatter diagram is the first step in correlation and regression analysis. It is a way to display the relationship between two variables, say x and y, graphically. It is the most common and easiest way of displaying visual picture of possible association between y and x. It shows the direction and strength of a relationship between the variables. Positive slope on the scatter diagram is associated with positive correlation, while negative is associated with negative correlation. However, it may not be useful for large sample sizes because relationship may be difficult to see with lots of points. The population correlation coefficient is usually denoted by P, rho, while its sample estimate is denoted by R. Interpretation of correlation coefficient R. Correlation coefficient R, rho, is interpreted both in terms of its value and its sign. Value of R. The value of R is always between -1 and +1. The size of the correlation R indicates the strength of the linear relationship between the two variables, say x and y. Values of R close to -1 or to +1 indicate a stronger linear relationship between x and y. If R is equal to 0, there is absolutely no linear relationship between x and y. No linear correlation. There may be a relationship, but it is non-linear. If R is equal to 1, there is a perfect positive correlation, and if R is equal to -1, there is a perfect negative correlation. Sign of R. The sign of the coefficient indicates the direction of the association, direct, positive, or inverse, negative. A positive value of R means that when X increases, Y tends to increase, and when X decreases, Y tends to decrease. Both variables change in the same direction. A negative value of R means that when X increases, Y tends to decrease, and when X decreases, Y tends to increase. As one variable changes, the other moves in the opposite direction. Pearson correlation coefficient. Pearson product moment correlation coefficient measures the strength of the linear association between two continuous variables. The correlation coefficient, R, developed by Carl Pearson, is a numerical measure of the strength of association between the two variables expressed as R is equal to n summation xy minus summation x summation y over square root of n of summation x square minus summation s square into bracket n summation y square minus summation y square. Assumptions. In order to apply Pearson correlation coefficient to investigate the likelihood, strength or degree of association between two variables, the following assumptions are expected to be met. The two variables, say x and y, must be random. These variables must be normally distributed. Linear pattern of relationship must exist between the two variables x and y. Limitations. Pearson product moment correlation coefficient is unduly influenced by outliers, unequal variances, non-normality, and non-linearity. Spearman's rank order correlation coefficient. An important competitor of the Pearson correlation coefficient is the Spearman's rank correlation coefficient. Spearman correlation coefficient is applicable when the assumptions of Pearson correlation coefficient is not satisfied. It is calculated using the ranks of the data rather than to the actual data value themselves. In so doing, many of the distortions that plague the Pearson correlation are reduced considerably. Spearmans look at whether or not there is linear relationship between the ranks of the two variables. The most common formula expression for Spearman correlation coefficient is shown as R is equal to 1 minus 6 into 6 summation D1 square over n into bracket n square minus 1, where D is the difference between the ranks of variables x and y, n is the number of pairs of observation x and y. Regression analysis. Regression is a statistical technique for finding a straight line that summarizes the information in a group of data points. We often refer to a regression line as a best fit line, meaning it is the line that is calculated comes at as close as possible to all the points. In this way, regression analysis produces an equation or model that describes how the variables in the data are mathematically related to each other. It can be used to evaluate the relationship or trend between two continuous variables. This analysis is defined for situations where a variable is thought to be related to one or more other measurements made on the same subject. So, it is a statistical tool that utilizes the relationship between two or more quantitative variables so that one variable can be predicted from others. Assumptions of linear regression equation. The following are some basic assumptions of applying linear regression analysis. The pairs of observation, dependent y and independent x variables are independent. These variables must be normally distributed. The relationship between y and x are truly linear. For a given independent variable x, y is normally distributed and the variance is the same at each value of x. The outcome dependent variable y is a random variable and x is measured without error or minimum error. Simple linear regression. Linear regression analysis is a statistical method of finding a straight line that summarizes the information in a group of data points to know how two or more numeric variables are related. The linear regression analysis performed with a single predictor independent variable is called simple linear regression. Simple linear regression therefore quantifies the association between two variables. Like correlation, linear regression methods are used when both y and x are continuous. The simple refers to a regression with only one x variable. The goal in simple linear regression is to see if there is a relationship between y and x, and often estimate a predicted value of y for a given x. Simple linear regression equation. The mathematical description of evaluating the relationship between two variables results in an equation called best fit line, expressed as shown below. Y equals to intercept plus slope x. Y is equal to beta naught plus beta 1x, where beta 1 is equal to n summation sy minus summation x summation y all over n summation x squared minus summation x squared, and beta naught is equal to y bar minus beta 1 x bar. Values of beta naught and beta 1 interpretation. The intercept of the best fit line beta naught is the expected value of the dependent y variable at zero level of the independent x variable. The slope or regression coefficient beta 1, on the other hand, tells us how the dependent variable y changes for every 1 unit increase in the independent x variable. On average, if the slope beta 1 is equal to 0, there is no relationship between x and y. If the slope beta 1 is equal to 0, the equation reduces to beta naught, which is the mean of y. In summary, beta 1 is equal to 0 implies that there is no association. Beta 1 greater than 0 implies a direct or positive association. Beta 1 less than 0 implies an inverse or negative association. Summary of study section 8. In this study section, you have learned that correlation coefficient is a numerical measure of the degree or extent of linear relationship between two quantitative variables, say x and y. Correlation coefficients are useful statistics for several reasons. They do measure the strength of a linear relationship between two variables, which can support a hypothesis about a cause-effect relationship. Correlation coefficients can be used to determine whether two predictor variables, such as two different exposures, are highly correlated to each other. Pearson product moment correlation coefficient measures the strength of the linear association between two continuous variables. An important competitor of the Pearson correlation coefficient is the Spearman's rank correlation coefficient. Spearman correlation coefficient is applicable when the assumption of Pearson correlation coefficient not satisfied. It is calculated using the ranks of the data rather than to the actual data values themselves. Regression is a statistical technique for finding a straight line that summarizes the information in a group of data points. We often refer to a regression line as a best fit line, meaning it is the line that is calculated comes as close as possible to all the points. Linear regression analysis is a statistical method of finding a straight line that summarizes the information in a group of data points to know how two or more numeric variables are related. Now we've come to the end of study section 8. Thanks for listening.